Hi, this is AK presenting you a free 1-hour video tutorial on MATLAB basics. Welcome to this video course titled MATLAB Basics in 1 hour. My name is AK. I am an aerospace and control systems engineer with several years of experience as a research and development engineer in the industry. MATLAB is a very powerful numerical analysis and mathematical modeling software that's being used by students, researchers, scientists, and engineers in the fields of physical and life sciences. To make full use of this video course, please download the course files from the link given in the show notes below. You don't absolutely need the files to understand the course, but if you download the free course material, you can follow along with me while I'm actually going through the video lectures. And you can make changes to the MATLAB files, experiment, and thus learn better. I recommend it. Unzip the contents to say your desktop. And after unzipping, you should see a folder structure that looks like so. I have divided this video course into 7 easy sections. There is a subfolder for each section. The particular subfolder will have all the files that you need for that section. I have tried to introduce MATLAB basics using interesting and practical examples from real-world science and engineering instead of boring, trivial hello world examples. I have also tried to get those example applications from diverse fields such as fighter plane dynamics, satellite failure analysis, rocketry equations, pharmaceutical drug potency analysis, artificial eye modeling, electromagnetic wave propagation from physics, earthquake response of a tall building from civil engineering, predator-prey population modeling from mathematical biology, and modeling the behavior of a stock price movement from financial engineering, and CAT scan image analysis, etc., etc. Let's get started. If you want to open the files for lesson 1, change the folder from MATLAB like so. And here are the files for lesson number 1. Just double click on the first file. Okay, when you fire up MATLAB, the user interface looks like so. The most important panes or the sub windows are the command window here and the editor window here. And this pane, which is the current folder, it is self-explanatory. And the workspace, we will actually talk about it in a bit. And the command history is also self-explanatory. Whatever commands you type here, it actually remembers the commands that you typed in, and you can actually go back and actually execute them by just double-clicking on the commands. All right, so let's first talk about the command window. The command window you can actually use as a very overpriced calculator. Like for example, we can say x1 equals 2. And you can say x2 equals x1 to the power of 3. And a slightly more sophisticated method is you can define, for example, vector 1 equals 1, 2, 3, 4, 5, and vector 2 equals 10, 20, 30, 40, and 50. All right, so you can actually say figure plot V1 versus V2 and grid on. So this is the V1 vector and this is the V2 vector. Okay. One of the most common ways you will probably encounter MATLAB is through the need for plotting data stored in a file. For lesson number 1, imagine your boss asking you to plot the aerodynamic variables of an experimental fighter jet. The test pilot has flown some maneuvers and the flight computer has collected and stored the following variables of interest: time, elevator deflection, forward speed change, and the pitch rate change, And lastly, the pitch angle change. This text file has the data from some experimental flight runs. By the way, you can actually open a .text document in MATLAB. You just double click on it and you just look at it. It looks like there are 6 rows and there are several columns. It actually goes on and on and on. The first row is actually the time vector, and the second row is the elevator deflection in degrees. And the elevator is actually, let me just show you what it is. Okay, so the elevator is this control surface, and it actually goes clockwise and counterclockwise. That's the input to the experiment. And the third row is the speed change in feet per second. And the fourth row is the angle of attack change in degrees. Okay, and the angle of attack is actually defined like this. The angle of attack is the angle between the chord line and the forward velocity vector. And the fifth row is the pitch rate change in degrees per second. The pitch angle, to begin with, is actually defined as the angle between the horizontal line and the chord line. And the pitch rate is the rate of change of this pitch angle. Okay, so this is the pitch rate. And finally, the sixth row is the pitch angle in degrees. Okay, all right, so you have a text file that has these variables of interest. This is the time vector, and this is the input to the experiment, and this is the response of the aircraft. The flight computer actually records all of this. So what you want to do is you just want to write a script that can load this text file and just plot these variables on different figures. So the first thing you want to do is read this text file. It's a very simple command, load, and this is the fighter plane data.txt is the name of the file. Okay, also notice that this text file is in the same folder as the script. Okay, this load command, it actually reads a text file and it actually stores it as a matrix, and this D is actually as a matrix. I'd like to show you how. CLC, clear the command line, and clear variables. It actually clears the workspace, and you can actually put a breakpoint by just left clicking on this number line and just say run. All right, so we have run up to this one. Notice there is nothing here on the workspace, and I just step, which is I click on step, and it actually executes this line, step, and the text file has been read and it is stored in the variable called D, which is a matrix. Let's actually double click on it. So this is the first line, first row, which is the time vector, and this is the elevator deflection in degrees. This is the speed change in feet per second, and this is the angle of attack change in degrees, and this is the pitch rate change in degrees per second, and this is the pitch angle change in degrees. Okay, so this has been loaded into the workspace, and what we want to do now is step. It actually creates a figure, and we are saying plot the first row and all the columns against the second row and all the columns. Let me just explain this a little bit. So if you just click on D, this is the time vector, and this is the elevator deflection. So what we want to do is the first row, this is the first row, and these are the columns, 1, 2, 3. So take the first row and all the columns. Okay, that's actually the time vector. That's the x-axis, and the y-axis for this plot should be the second row and all the columns. That's what we mean by this statement. This is the row number, comma. This semicolon means all the columns. So we are taking the first row, all the columns, and this is the x-axis variable, and the y-axis variable is the second row, all the columns. And this dash B means a solid line, give me a blue color. All right, so y limit 10 to 25 is limit the y-axis values to between 0 and 25, and title, x label, and y label, they are actually self-explanatory. All right, so I'll actually put another okay, let me just step through this code. Okay, this is how it actually looks like. Time versus elevated deflection. All right. So in the next set of commands, I'm actually plotting the speed change, and in this block, I'm actually plotting the angle of attack. The code is the same. What has actually changed is x-axis is the time, and y-axis is actually the third row and all the columns, and so on and so forth. Let me just run through it. So just say continue. So this is the pilot input, okay, elevated deflection, and the experiment has been run for 30 seconds, and this is how the speed changes because of this elevated deflection during this 30 seconds test interval. And this is how the angle of attack actually changes, and this is how the pitch rate, remember the pitch rate is the rate of change of the pitch angle, and this is the pitch angle change itself. That's it. If you want to make the plots look a little bit pretty, I have another script here. So what you can do is close all. It actually closes all the plots, and you can say clear variables, and you'll see all of the variables in the workspace. They'll actually be deleted. You can actually run 1 hour MATLAB 01 plot 5 to plane data professional plots. So in order to run this .math file, you can actually click on this button, or you can say, you can copy and paste this value, the name of the file, and press enter. Okay. As you can see, the plots are professional grade. Now you can publishing quality. Okay. Again, time versus elevated deflection, speed change, angle of attack change, pitch rate change, and pitch angle change. So that's it for the first lesson. I hope you found this video useful. Thank you. Hey, AK again. Welcome back to video number 2 in the 1 hour MATLAB series. In this video, we will explore the array operations and array indexing in MATLAB. MATLAB is very efficient when dealing with vectors and matrices. Knowing how to read, write, and manipulate arrays using indexing operations is an important and extremely useful skill for MATLAB programmers. As usual, I'll start with the practical example to illustrate array operations. Say there is a space probe that has 2 transponders, okay? The main transponder and the backup transponder. The backup transponder will kick in only when the main transponder fails. Under normal operations, say the signal from the main transponder is around 4 microvolts. Okay, suddenly the space probe's control system malfunctions and it starts spinning wildly in space. The signal from the main transponder, instead of being more or less a steady signal, now shows severe oscillations. So the signal actually looks like this. So under normal conditions, we are actually seeing approximately 4 microvolts plus some noise. The failure actually happens here. The control system fails here, and the satellite starts oscillating uncontrollably. The probe is actually spinning uncontrollably. Disaster strikes again. After a few seconds, the main transponder is actually ripped off, and the signal from the main transponder flatlines to 0. But again, redundancy kicks in, and the secondary transponder immediately starts broadcasting its signal. So the situation looks like this. So, operation normal, 4 microvolts approximately with some noise. Satellites start spinning out of control, and this is the signal from the main transponder. The main transponder is actually ripped off here. The secondary transponder kicks in, and remember, the satellite is still spinning out of control. So the secondary transponder actually gives out the signal. Okay, so this is the situation now. You are part of the satellite telemetry group, and your failure analysis team captain asks you to stitch these 2 signals together, which means take this signal and stitch it with this signal so that you can create something useful for the failure analysis team to do some math on. So that's the task. So the text file that's actually being provided to you is the satellite failure data.txt. Double click on it. This is the familiar structure that we saw in the previous video. You have 3 rows, and the first row is the time, the second row is the signal from transponder 1, and the third row is the signal from transponder 2. All right, placing a breakpoint here, running, and just step. Okay, so we read the text file into this matrix. Again, this is time, this is signal from transponder 1, signal from transponder 2, known stuff from video 1. For convenience sake, I'm actually creating new variables. Time is, take the D matrix, first row, all columns. Signal 1 is again D matrix, second row, all columns. Signal 2 is third row, all columns. Okay, so we'll execute this line by line. Step, step, step. And I just want to plot the signal from transponder 1 and transponder 2. We have a new command here, subplot. Let me just explain this. Again, figure. Okay, let me execute this command and you'll know what I'm talking about. Step. Okay. So what this actually has done is we need 2 rows in this figure, one figure, 2 subplots, that's what it means, and 2 rows, 1 column, and this one means the first figure. Okay, so what you have done in the first subplot is we have plotted time versus the transponder 1 signal. All right, and you know where this is actually going. Step, 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 and this is subplot. 2 rows, 1 column, the second subplot. We have plotted the transponder number 2 signal. All right. So, okay, now we come to the important part, which is the find command. All right. So before I execute this line, I just want to give you some graphical explanation as to how the find command works. All right. So the MATLAB find operation. In order to understand this, let's actually start with a vector v. Let's say this has 5 elements. This is the index 1, index 2. Note that the index is not the same as the element. Index is the place value of this element in this vector. So this, what we're saying is index 1 means is the first element. Index 2 means this is the second element. Index 5 means the 5th element. So if we execute the command, if we ask MATLAB to find the indices of all the elements that are greater than 4.0, what will happen is, okay, so MATLAB's answer will be index 4, index 5. So what MATLAB will do is, okay, it will come to the first element and it will check whether this element is actually greater than 4, which is not. This element also fails the test. Third element also fails the test. The fourth element is definitely greater than 4.0, so its index, which is number 4, 1, 2, 3, 4, will be part of the answer, but it is not the full answer. So the MATLAB will keep continuing and it will say, okay, this element is also greater than 4, so it will, the answer will have index 4 and index 5. Now we can qualify the find command with the condition saying that find the index of the first element that has value greater than 4.0. In this case, MATLAB's answer will be, it'll keep on checking the condition, and when it reaches the 4th element, this element is greater than 4.0, it will return the index, and that's it. MATLAB will give you the answer as 4 because you have qualified the find command with the condition that give me the first element that has value greater than 4.0. What we are saying is we are defining a new variable called index, and we are saying take signal 1, which is the transponder signal 1, okay, and find the first element. Okay, if I bring in, okay, this is the transponder signal, signal from transponder 1, and find the index of the element which has the value 0. That's what this command means. All right. Once we do that, we create a truncated version of signal 1 from start to the failure time index -1. Why -1? We don't want the element, we don't want the index where it actually goes to 0. We just want the index, just one index before transponder signal actually goes to 0. So we want to snip the signal from this index to this index. That's what this statement, this line is actually doing. We are creating a new vector. Signal 1 truncated is signal 0, 1, which is the original vector, and you are taking part of the vector that starts at index 1 and actually goes up to index -1. Index, we found it using the find command, right? So what we're doing is we are snipping, cutting the signal from this point up to this point. So that's signal 1 truncated. And signal 2 truncated is we take this signal 2 and we truncate from this index up to the end. So what we're doing is we are cutting the signal 2 from index, which is this one, up to the end. Okay, now we are creating a new vector called signal new, and we are actually concatenating signal 1 truncated with signal 2 truncated. Okay, I just want to show you. Okay, step. Okay, all right. Some interesting stuff here. If you say, if you type in length signal 1 truncated, it actually gives you answer 129, which means signal 1 truncated, which is from here to here, we have 129 elements, and signal 2 truncated has 171 elements. So if you combine this with this, we should have $300, right? So 129 plus 171 is 300. So what you have actually done is we have taken one truncated vector and we have concatenated this with the other truncated vector, and we actually created a new one. All right, we'll actually create a new figure and plot the new signal vector step straight on. So this is how the new vector looks like. So we have actually taken part of the transponder, the useful part of this transponder signal, and we actually concatenated this with the useful part of the transponder 2 signal, and we actually created a new signal. That's what this plot is about. And the final plot is, it is just a sanity check. I'll actually show you what's actually going on. Okay, so what we've actually done is we are actually over plotting. So first we plot the signal new, which is this one here, the concatenated signal, and we're actually plotting signal 1 in black. There is a new command here, it says hold on. So what we are saying is we plot the first signal, and if you don't type in hold on, when we do the plot again, the first signal will actually disappear. So this actually holds the plotting, so we can overplot. So hold on means it helps us to overplot. So signal 1 is actually plotted in black. It actually comes down here, and signal 2 is actually plotted in blue. So they're actually right on top of each other. So we know our snipping operation, and snipping and joining operation has gone flawlessly. All right. So that's it for this video. I hope this was useful, and we will meet in the next video. Thank you. Hey, AK again. Welcome back. This is the third video in the series 1 Hour MATLAB. In this video, we will take a look at MATLAB functions. Whenever you're doing certain tasks repeatedly in your code, it is time to wrap those lines of script inside a function. As usual, we will start with a practical example to illustrate the concept and set up the problem before we jump into MATLAB coding. Imagine you are a scientist working in the modeling and analysis section of a private space launch company. Your department is actually given a data file that actually that contains launch data from an actual rocket flight. By the way, a disclaimer, this is a fictitious scenario. I haven't used any data, classified or otherwise, from any actual rocket. This is purely fictitious data for illustration purposes. The data file this time is not a text. Let's go to MATLAB. So the data file that we are talking about is not a text, or in other words, ASCII file format. Rocket launch data.mat. This is a MATLAB binary file format. Okay. Humans can't read this file format, but computers can, and this format is very efficient compared to the ASCII file format, especially so for large data sets. Okay. And this rocket launch data.mat, it has 5 data elements. The first one is a float, Earth radius in meters, and the second one is a vector of floats, time vector, and the third one is the rocket height. It's again it's a vector of floats, and this one is the rocket airspeed, again a vector of floats, and the last data is a launch angle, which is again a vector of floats. Okay, so this is the vertical line, and this line is actually approximately the way the rocket nose is pointing. So the launch angle, again, roughly speaking, not very precise in aerodynamic definition, is the launch angle is the angle between the vertical line and the way the nose is actually pointing. Okay, so that's the launch angle. And the first thing we want to do is to understand how these variables of interest are actually evolving over time. We just want to plot the data from this file and understand how the variables are actually behaving. Okay, so we open this 1 hour MATLAB 3 rocket launch analysis, which is the main script for this this video. And the first thing we want to do is actually load rocket launch data.mat. All right. So put a breakpoint here, run. I'm going to go a little bit faster because this is all known stuff. And step. Okay, this is all plotting stuff to make the plot look pretty. So don't worry too much about it. Just concentrate on, once you actually execute this load command, observe here in the workspace, and we have all the data variables loaded into the workspace with the proper names. We have in alphabetical order, right? So we have the Earth radius, which is a float, and all of the other variables are just a vector of floats, just as I described. Okay, so I'm just going to place a breakpoint here and just say continue. We run up to this point, and this is actually known stuff. In a subplot, we are actually plotting the rocket height and the rocket airspeed and the rocket launch angle, which we talked about before. So I'm actually going to set the breakpoint here and actually say continue. And this is how the rocket launch variables actually behave. Time versus rocket height, time versus rocket airspeed, and time versus launch angle. Now it starts pretty close to 90 degrees, which is approximately vertical. Then the launch angle actually gradually comes down. So this is all well and good. Okay, so what we want to do in this video lesson is understand a little bit more about how MATLAB functions work. Okay, now that we have an idea of how the important rocketry variables of interest evolve over time during the launch, say the optimization group in your company wants to know the instantaneous mass at any given instant during the launch. Okay, what is instantaneous mass? Fire up Photoshop again, and okay. So when the rocket is being launched, a tremendous mass is actually being lost in the form of burnt fuel, and the mass of the total rocket system is actually changing every second. Okay, so the instantaneous mass is given by this equation, 1875 minus 1.997 multiplied by the time instant. By the way, this equation will vary depending upon the rocket configuration. So this equation is not for this particular rocket, but for a fictitious rocket. All right. Okay. So using Newton's classical mechanics, you come up with the formula for the instantaneous mass of the rocket, which is this equation here. And this is just crying out for a MATLAB function. Okay, so say your rocket modeling group or the trajectory optimization group in your company wants to just input the time instant. Okay, and the function that you write, it needs to output the mass of the rocket for that instant. Okay, so let's go back to MATLAB, I just want to show you the function calculate instantaneous mass. Okay, so look at the function syntax. The name of the function is calculate instantaneous mass, inst mass. It has one input argument and it has one output. Note, input is actually contained between normal brackets and the output is actually contained between square brackets. So it takes one input and uses this equation, and this is the output. So it's pretty simple to understand. So the MATLAB function syntax, it's easy to understand. All right, how do we use this function in a script? So let's say I just want to say close all and clear variables, and I'm going to put a breakpoint here. I'm going to run the script. Continue. Okay, we got the figure. Not yet. Okay, there you go. Continue. All right, this is the figure that we talked about earlier, and this is where in this section I'm actually calling the function. So your optimization group is actually telling you find the instantaneous mass of the rocket at time instant equals 100, and we want to see whether we have data for the exact time instant 100. If you just go to the time vector, so if we don't have data for exactly 100 seconds, but somewhere close, 101.76 seconds. So what we will do is we will set time instant equals 100, and we want to find the vector index that is closest, greater than or equal to time instant, and we just want to find the first element. Again, this is all known stuff. So if we execute this line, step and step, the vector index is actually 35, right? 35. So we found this element, okay, and the vector index is 35, and the time instant is 101.7640, which is pretty close, which is the closest as we can get to 100 seconds. All right. Then we find that with the element in the time vector which corresponds to this vector index, which is 35, and we said that it is 101.76 seconds. So that's the input argument. And if you want to step into the function, you can say step in. You go into the function, and this is a pretty simple equation. It takes the input argument, calculates the instantaneous mass, and actually comes back. All right, and this line, this just prints the instantaneous mass and the time instance to the command window. All right, so now your group, optimization group, is actually calling for another function. They're telling you, I want to give you the time instant, and you tell me, you calculate the drag, the instantaneous drag for the rocket at the time instant. And you write another function, calculate instantaneous drag, that actually takes 3 input arguments and returns 1 output argument. Okay, so it takes the rocket height, the rocket speed, and the earth radius. And how we call that one is, again, same as before. Let's say this time we want to find the instantaneous drag at 120 seconds. We find the vector index, and we find the height. Okay, so we find the element from the height vector that actually corresponds to this vector index. Again, we find the element in the airspeed vector that corresponds to this vector index, and the earth radius. And you will understand why we need the earth radius in a second. So we step into the function. Okay. Now, the height of the rocket in the equation that you developed is the height from the center of the Earth. So in order to find the atmospheric height, you need to subtract the earth radius from this height variable, and this is height above ground. Step, and this is the drag equation we talked about. We are implementing this equation in MATLAB. This is the exponential part, and this is actually the quadratic part. And step. All right. And this is again printing to the command window. So for the time instance, we don't have data for exactly 120 seconds, but we found the closest match, which is 120.664 seconds. The drag at this instant is this many newtons, because drag is a force which is being measured in the SI system in newtons. Now I want to talk about MATLAB functions that can actually accept multiple inputs and give out multiple outputs. And let's go take a look at this new function called calculate mass and drag. Again, the optimization group actually tells you, hey, I will give you the data file for the rocket launch, and I'll give you the time instant of interest you calculate the instantaneous mass of the rocket and the instantaneous drag of the rocket at that time instant. Now, you can call this MATLAB function from the command line like so. You can call it from a script too, but I just want to show you how we can call a function from the command line. Okay, so the first argument is the data file, and we give the name of the data file, within quotes, rocket launch data.math, and the time instant that we're interested is 110 seconds. And the function, note that it has two output arguments: instantaneous mass of the rocket, instantaneous drag of the rocket. Okay, and let me put a breakpoint here, and if I just execute it from the command line, we will stop here. We are loading the data file. This is known stuff, and finding the vector index, this is also known stuff. We talked about it, right? We find the time instance, and we find the height, rocket height, and rocket height above the ground, and the rocket speed. And once we know these variables at the time instant, we can calculate the instantaneous mass of the rocket, and we can calculate the instantaneous drag of the rocket using this equation. And notice, once the function is done executing, the output arguments are actually being printed to the command window. Mass of the rocket at that time instant is 1.6502 10 to the power 3 kilograms, and the drag is 3.0961 10 to the power 5 newtons. All right. Okay, so that's it for this video. I hope this was useful, and I will see you in the next video. Thank you very much. Hey, AK again, welcome back. This is video number 4 in the series called 1 Hour MATLAB. In this video, we are shifting gears up a little bit, and we're going to look at the topic of curve fitting in MATLAB. The need for curve fitting comes up many times in both life and physical sciences. Since we have been concentrating heavily on aerospace and rocketry in the previous videos, I thought we will look at a practical example from the biotechnology field in this video. Imagine you are a scientist developing a new drug against a dangerous strain of bacteria. You are testing the potency of your new drug upon a petri dish full of bacteria colonies. You are measuring the quantity of bacteria that are alive against the drug concentration. The drug concentration is plotted along the x-axis. The bacteria quantity is measured in the units of CFU per plate, or colony forming units per plate. This is the raw data. This on the x-axis is the drug concentration measured in micrograms per milliliter, and on the y-axis is the colony forming units bacteria per plate. So looking at the raw data again, we have the data for 0, 5, 10, 15, 20, 25, 30, and 35. 0 is, by the way, the reference reference value, which is. But the question is, what if you want to find out the CFU, the bacteria quantity, for a drug concentration of 7 micrograms per milliliter? We don't have the data. All right, so we just have the data points for these individual drug concentrations. But another colleague of ours, might want to find, okay, if I set the drug concentration to 7 or 16 or 31, whatever, what will be the colony forming units per plate bacteria? And this is where the curve fitting actually comes in. And what we are looking for is to get a curve, which is the dotted T line here. And given this X and Y data, we want to mathematically find a curve that actually passes through, in other words, almost passes through these points and approximates this shape. Okay, that's actually curve fitting. This is a typical scenario. You have the raw data in actually yellow, and we want to know the bacteria quantity for a drug concentration of 7 micrograms per milliliter. Okay, we don't have the data, but if we have the mathematical equation for this curve, we can just go up like this. For this drug concentration, we can say this will be the bacteria quantity. So this, in essence, what curve fitting is all about. Okay, so again, what we need is to find a math equation for this dotted T line, and we need MATLAB's help to do that. All right, there are multiple ways of doing curve fitting, and we can use different types of mathematical equations to do the curve fitting, to find this mathematical expression for this curve. Today I'm actually going to talk about a specific set of equations called polynomial equations. So a first degree polynomial it should be very familiar to you. This is nothing but a linear equation. Why the output is a0 plus a1x. a0 and a1 are called the polynomial coefficients, and the second degree polynomial equation should be a0 plus a1x plus a2x square, and so on and so forth. And for the nth degree polynomial, the equation is a0 plus a1x, etc., up to an x to the power of n. So we will use a polynomial equation to do the curve fitting. And the problem at hand is we know the y and the x data. We want to find these coefficients a0, a1, a2 up to an using MATLAB. Okay, let's fire up MATLAB. This is the x data and this is the y data, and you already know how this looks like when we plot it. This is the raw data, x and y. Let's put a breakpoint here and actually run it. Alright, this is the familiar plot that you've been looking at so far. Now, again, what we want to do is we want to find a polynomial equation for this shape in MATLAB. Alright, the way to do that is using a command called polyfit. So what polyfit does is it takes the x data and it takes the y data, and it's trying to fit a sixth order polynomial to this data. So this is the sixth degree polynomial whose coefficients we are trying to estimate using MATLAB. MATLAB actually takes in the x data and y data, and it will calculate a0, a1 up to a6. That's the problem at hand. And the command that we use for that one is polyfit. And the polyfit command takes the x data and the x vector, which is this one here, and it takes the y vector, and the third argument is the degree of the polynomial. Recall that the degree of the polynomial is, in this case, it is actually the degree is 6, which means we are looking at a polynomial that looks like this, a 6th degree polynomial. All right. Okay, let's run the polyfit command, just executing just this line using step. So this is what MATLAB has returned, and these are the coefficients of the polynomial. By the way, this is actually a6, a5, a4, a3, a2, a1, a0. The coefficients I'm talking about is this one. So MATLAB actually returns them in the reverse order. a6 is actually returned first, a5 next, etc., and a0 last. So if we come back to MATLAB, this is a6, this coefficient here, and this one is a0. All right, coming back to MATLAB again. So we have this set of polynomial coefficients, right? So how do we use this to solve the problem at hand, which is we want to know the amount of bacteria for a drug concentration of 7 micrograms per milliliter. Recall that was the original question, right? That led to this polyfitting quest. So we know the x value, which is 7 micrograms per milliliter, and we just want to find out, okay, what will be the y value, and how do we use the polynomial coefficients that we just got from MATLAB to solve this problem? It's pretty simple. We need to use another MATLAB command called polyval, and the way to solve this problem is you input the new x value, which in this case is actually 7, and the first argument is, of course, the polynomial coefficients vector, p a6, a5, etc., up to a0, and the second command is the x value, and MATLAB returns the y value using this polynomial equation. So let's just run this step, and the y new is 3.039. Let's actually do a format change. and 309.3909. Okay, so if you just go back to the plot here, what we're saying is for a drug concentration of 7 micrograms per milliliter, we will have approximately 309 CFU per plate. Okay, so this is how we use the polynomial coefficients that the MATLAB actually given us. Okay, so now I'm going to do a different operation. I just want to see, using these polynomial coefficients, I just want to see how good is the fit, how good is the polynomial equation trying to approximate the raw data that we actually sent in. In order to do that, I'm going to create a new vector x1, which is set equal to the original x data, which is this one. And I mean, you don't have to do that, but I'm actually doing it for clarity of nomenclature. So this is the x vector, and I'm using again the polyval command. And notice this time, p is just the polynomial coefficients. Okay, notice this time the x value is not a single float. It's actually a vector of floats. Okay. In this case, it is the x data that comes in. It's a vector, and if you execute the polyval command, okay, the output of the polyval will be a vector. So let's execute that step and step, and y1. Okay, so we can actually plot this, which we're going to do in this set of commands. Just say continue. And this is what we get. So the yellow data is the original measured data, and the purple line is what we get using the polynomial equation using the polynomial coefficients that MATLAB just gave us. As you notice, the fit is not 100% perfect. That's okay. We can keep increasing the order of the polynomial equation, and we can get closer and closer to the original data. This is a push and pull between how close you want the polynomial coefficient to be to approximate the data points against what is the complexity that you can live with when it comes to the mathematical equation. The more polynomial coefficients you have, the more complex the equation becomes. And at some point, you'll have to actually take a scientific or an engineering decision. Okay, I'm stopping here. For this specific problem, I found that a 6th degree polynomial is more than enough to do the job, and I'm just accepting a 6th degree polynomial. Okay, so this is how you do curve fitting in MATLAB. And this technique, using a polynomial equation, polynomial curve fitting, I use it again and again in my professional life. And this is a very useful technique. I hope you also found this useful, and thank you very much for watching. I will see you in the next video. Hey, AK again, welcome back. This is video number 5 in the series called 1 Hour MATLAB. In this video, we are attacking a slightly more difficult problem. We are going to numerically solve a differential equation in MATLAB. If you're a bit rusty on your differential equations, don't worry. I will give you step-by-step explanations. We are again taking a practical example from biotechnology. Say you are a researcher working on an artificial eye, and say you want to match the response of your bionic eye as close as possible to the human eye. Okay, so let's look at the response of a human eye to a light stimulus. X-axis is time, and the red line is the light stimulus. That actually goes from 0 to whatever a constant value k instantaneously. So this is constant for all time. But the response of the eye, which is in yellow, it's not instantaneous. It takes a while for the eye to respond. Okay, we call the input light stimulus as u of t, which is a function of time, and the response of the eye as x of t, which is again a function of time. So this response of the eye, it can be modeled as a differential equation. What is a differential equation? Notice that the eye response is not given as an algebraic or a trigonometric equation. It is given as a differential equation. What we are saying is the time derivative of x of t, which is the I response, is equal to some constant multiplied by the I response itself, plus again some constant multiplied by the input light stimulus. So notice that in the differential equation, the time derivative of the variable of interest is also involved. Okay. Oh, by the way, many of the physical and biological systems, they can be modeled as differential equations. Okay. This particular equation, which is called first order linear differential equation, and this has a neat analytical solution. Remember, this is the differential equation, and if you solve a differential equation, you get another equation. If you solve, say, an algebraic equation, say for example, a second order equation, right, quadratic equation, you can get two values as the solutions. But recall, if you solve a differential equation, you get another equation as the solution. In this case, this has a very neat analytical solution. The I response is given as an exponential equation. So k multiplied by 1 minus e to the power minus t by tau, and the response, the x of t with respect to time, it looks like this. Let's actually fire up MATLAB, and before we solve this differential equation numerically, let's plot the analytical solution. Open up 1 hour MATLAB 05 iresponse.m, and this is the iResponse gain, and these are the two constants that I talked about. This is just some plotting stuff, ignore this. And let me just put a breakpoint here. So we are looking at the analytical solution first, and this is just the equation that we talked about, this equation here, and I'm just implementing this in MATLAB. Time vector is linspace 0, 100. This linspace is a very useful command. What I'm actually saying here is create a vector called a time vector, which has 100 elements, and it actually starts from 0 and it ends at 1. It has 100 elements and it starts at 0 and goes up. It's the second element is 0.01, third is 0.02, so on and so forth, until the final element is actually 1. So that's what linspace means. This is a very useful command, and this is just the implementation of the analytical solution for the differential equation. The rest of it is actually plotting stuff. So let me just plot it. This is the time vector and I response. Unfortunately, not very many differential equations have such neat analytical solutions. In fact, many differential equations that we encounter in physical and life sciences, they don't have neat analytical solutions, and we have to use a technique called numerical integration in order to find the response, the system response. Okay, I'll explain the numerical solution to you. Again, time axis, and this is the stimulus of the system u of t. This is known, and we start at time t0. Okay, so the input to the system u of t is known, which is k, and the system response at the start of the simulation, it's actually 0. So at time 0, we know u0, which is the system input stimulus. It's known, it's k, and we know the system output response, which is the I response, which is x0. That's known, which is 0. You take these two known values and use a numerical integration formula to find the system response at x1, which is the system response at time t1. So you go to the next time step, t1. We already know the input stimulus, which is u1, and we know the system response, I response, at t1, which is x1. You use these two, this known information here, and calculate the system response at time t2, which we call as x2, and you get the drift, so on and so forth, until we are actually done with all the elements in the time vector. So this is the general idea for solving a differential equation using a numerical integration. but there are very many methods to calculate the next calculate the response of the system for the next time step given the value of the input stimulus and the system response at that time instant. So one such method is called Euler's method. By the way, there are very many different methods of numerically solving differential equations, like Runge-Kutta, for example, and Adam Bashworth. Those are pretty advanced methods. In this video, I will be going through Euler's method because this method is the easiest to implement and easiest to understand. If you're interested in other methods, do drop a line in the comment section, and I'll create an advanced video on that one. Okay, let's talk about Euler's method here. This is nothing but the differential equation that we are trying to solve. And in order to understand Euler's formula, we have to rewrite this differential equation in so-called standard form. We are saying the left-hand side is still the same. It's just the time derivative of the system response, d by dt of xt equals. We are writing the right-hand side as f of x of t, the system response, and u of t, which is the system input stimulus. Okay, so nothing new here. What we are saying is the right hand side is a function of x of t and u of t, which is true because the first part of the left hand side is a function of x of t, and the second part of the right hand side is a function of u of t. Okay, this is just a mathematical convenience. And given we have written the differential equation in this format, Euler's method is actually given by x of t of 1, which is the system response at time instant 1, is given by the system response at time t0 plus delta t. Remember, delta t is the difference between the successive time instants. So again, Euler's method is the system response at time t1 is equal to the system response at time t0 plus delta t multiplied by the f of x of t0, time instant 0, and f of u of t0. That's Euler's method. Let's see how that actually works in practice for this differential equation. Okay, I'm going to apply this Euler's formula for time instant 1. X of t1 equals x of t0 plus delta t multiplied by f of x of t0. F of x of t0 is nothing but this part evaluated for time instant t0, which is nothing but minus x of t0 divided by tau, and this one is just the right hand side, the second part evaluated for time instant t0. So all we do is we just substitute t0 here, and we get the system response for time instant t1. You get the drift. For the system response at the time t2 is, we already know x of t1, we just substitute here, plus delta t multiplied by x of t1, we already know, we just substitute here, and u of t1 is already, it's known for all time. And if we evaluate the right hand side, we get the system response for the time instant t2. All right, let me illustrate this further. So at time instant t0, we know the system input stimulus, and we know the system response to be 0. So this is known at time instant t0. We want to find x1, which is x of t1, and it is given by x of t0 plus delta t, which is known, multiplied by, again, minus x of t0, which is known, tau is known, it's just a constant, plus k is also a constant, that's known, by tau, multiplied by u of t0. So if we evaluate this right hand side, we get the system response for x of t1, and again we go to time instant t1, and we evaluate the system response for at time instant t2 using this iterative formula. X of t2 is x of t1, which is already known here, and delta t minus x of t1, which is known, tau known, plus k by tau, a constant, multiplied by u of t1, which is known. So we keep on going through this iterative formula and keep on evaluating one step ahead at a time until all the elements in the time vector are exhausted, and at that time we are actually done with the numerical integration of this differential equation. Okay, all right, so the analytical part is actually done. We are coming down to the numerical solution, and we are setting, oh, by the way, the arrays in MATLAB, they start at 1, not at 0. That's why the first element in the system response, I'm setting it to 0. What I'm actually saying is this here, the system, the yellow is the system response. The system response at the start of the simulation is actually 0. That's what I'm actually saying here. And u vector is, I'm creating a vector that is the size of the time vector. It is just a vector of ones whose size is the size of the time vector, and I'm actually multiplying this with k. Okay, so it's k in this case is actually 1, but it can be any value in for other differential equations. So we are creating the u vector, which is the system input stimulus. And delta t, we talked about it. It is the difference between the successive time instance, and we are taking the second element in the time vector and subtracting the first element in the time vector to get the delta t, this delta t here. All right, so this is all easy to understand. And the gist, the important, the main algorithm is actually in this for loop. This is where we actually implement Euler's method. Okay, the system response at index 2 is equal to the system response at index 2 minus 1, which is 1. We already know, set it to 0, plus delta t multiplied by the rest of this stuff is just implementing this equation here. Okay, so we talked about it. So we keep on going through the loop until all the elements in the time vector are exhausted, and at this point we have the solution for the system response. And let me just put a breakpoint here. So this is the numerical solution, and in this part we are comparing the analytical solution and the numerical solution. Let me just, and we find that the numerical solution is the same as the analytical solution. Okay, so this is how you solve a differential equation numerically in MATLAB, and I hope you found this video useful. I will see you in the next video. Thank you. Hey, AK again. In this video we are trying to answer the question, is MATLAB programming easy to learn? My answer is a definite yes, and here are my reasons. It is easy to get started in MATLAB. You install MATLAB, you fire it up, and you're ready to go. And you can start solving problems right from the command line from the get-go. For example, let's say you have a quadratic equation 4x squared minus 25x plus 9 equals 0. You can solve this from the command line like so. You define a vector with the coefficients of the equation equals 4 minus 25 9, and this command roots will actually give you the solution for this quadratic equation. All right, as simple as that. There is no need to install compilers or linkers to create executables. Neither is there a need for installing any additional libraries for performing floating point math or special libraries for trigonometric, logarithmic, or matrix operations. It's all part of standard MATLAB. Likewise, you don't need to install special libraries for plotting. The standard MATLAB installation comes with an extremely powerful plotting library pre-installed. You can do a lot of scientific and engineering modeling, do sophisticated analysis on your data, and produce professional grade plots very quickly. MATLAB is an interpreted language, and it is not a compiled language. This means when you press the run button, the MATLAB script is almost instantaneously executed. So if you just want to run the script, just press run, and that's it. There is no need to compile and link your code to create an executable. Okay. And the next point I want to make about the ease of learning MATLAB is that MATLAB code is very human readable. I would say MATLAB coding is it resembles mostly C programming in syntax, except for array indexing and indexing matrices, which can be a little bit tricky to begin with. Once you get past those hurdles, just reading MATLAB code and writing MATLAB code is very easy. Next on my list is the superb MATLAB help system. You can type help on the command window, and MATLAB actually comes up with very good info on the syntax and suggestions for using MATLAB commands in practice. For example, if I want to get some more help on this command LSIM, which actually stands for linear simulation, just say help LSIM. It's very comprehensive help system. It actually tells you the input and output arguments, and it actually gives you the use cases. You can also go look at other commands that are in the same family, and you can actually look at the documentation for LSIM and other functions named LSIM, etc. So it's pretty comprehensive. In addition, you have the support system from the MathWorks, like the MATLAB Central. So you have the MATLAB Answers, the file exchange, where MATLAB practitioners actually upload complete examples. Some of these examples are really sophisticated. I have talked so far about the ease of using MATLAB. This does not mean MATLAB is a simplistic programming system. In fact, it is just the opposite. MATLAB is an extremely powerful scientific and engineering programming package. Even complex models and simulations can be created in MATLAB quickly and efficiently. I just want to show an example. All right. So you remember the fighter plane longitudinal dynamics from video 1. This is called the state vector. The state vector is the vector that has the variables of aerodynamic variables of interest. V is the forward airspeed, and alpha is the angle of attack, and q is the pitch rate, and theta is the pitch angle. And these are all time differentials. This is the time derivative of the forward airspeed with respect to time, and this is again, so alpha dot is actually d alpha by dt, and this is dq by dt and d theta by dt. And this is given by this big matrix multiplied by the state vector itself, plus this matrix B matrix multiplied by the stimulus inputs. So this is what we call a matrix differential equation, and this is written in the form dx by dt, where x is a vector, equals a, this big matrix, multiplied by the state vector itself, plus b, this matrix, multiplied by the input stimulus vector. So the solution for this matrix differential equation is given by this cryptic looking equation, which is again a matrix equation because x is a vector, and remember a is a matrix and b is a matrix. So this is a fairly non-trivial problem to set up and analyze, but getting the solution in MATLAB, it is really easy. Let me just show you. Open fighter plane longitudinal dynamics.m, and these are the matrices that I talked about, A, B, and C, D matrices, and this is all plotting stuff, just ignore. The main stuff here, the gist of the solution actually happens in these two lines. That's it. You create the so-called state space system with these four matrices, A, B, C, D, and this command, this innocuous looking command LSIM, which stands for linear sim, that actually solves this whole matrix differential equation. So this whole solution here is done by this single command here, LSIM. Let me just run this. That's it. Don't worry if you don't fully understand the math behind this. My intention was to show that relatively complex modeling tasks can be achieved very easily in MATLAB, and I just wanted to show you the power and elegance of MATLAB I hope this video was useful. Thanks for watching. I will see you in the next video. Hey, AK again. In this video, we are trying to answer the questions. What actually is this MATLAB software? And what is MATLAB being used for in the real world? And here's my take on that. MATLAB is a software that is used for modeling physical, engineering, biological, and financial systems, and also for analyzing and plotting large data sets using matrix math. Let's start with the modeling part first. Let's start with an example of a system modeling from physics. I'm going to talk about the propagation of electrical and magnetic fields, or in short, electromagnetic fields in space by using the following famous Maxwell's third equation. This is the Maxwell's third equation in differential form. We read this as this inverted triangle followed by a multiplication sign as the curl. So we read this as the curl of this electric field. This E is the vector electric field and B is the vector magnetic field. So we say the curl of the electric field is the negative of the partial derivative of the magnetic field with respect to t. Also remember, both E, the electric field, and B, the magnetic field, they are functions of both the time and space. So we can model this equation in MATLAB and we can actually plot the distribution of electric and magnetic fields, in short, electromagnetic fields in space. Fire up MATLAB, go to folder number 7 and load up the script called What is MATLAB Used For? The actual physics application starts here, Maxwell's third equation in point and differential form, and we're going to solve this equation in MATLAB, and we're going to plot the distribution of the electromagnetic field in space. So three-dimensional space, electric field, magnetic field. All right. Okay, we are looking at an engineering application in MATLAB. Imagine a tall building which is being subjected to an earthquake, and the response of this tall building we are going to model in MATLAB, and I'm going to show how it's usually done by earthquake and civil engineers. So the acceleration due to the earthquake, it can be easily measured with sensors, and the building is actually modeled as a set of connected masses, masses connected by springs, and we can create a model for this mass and spring system using the second order differential equation, md square x by dt square plus kx equals a of t, where m is the mass matrix. It is the matrix of all the nodal masses, and x is of course the node displacements, so it contains the displacements for all of these nodes, and k is the stiffness matrix for the springs that are actually connecting these nodal masses, and a is the acceleration vector, that is the input stimulus. And we have talked about differential equations like this, in the previous videos. So we use similar techniques and we actually solve for the displacement of these nodal masses. Now I'm going to talk about an application in biology for MATLAB, and let's actually talk about an ecosystem where we have predators and prey. Say for example wolves and deer. Predators and prey populations are interdependent. Wolves actually start eating too much of deer, the wolves population go down, the deer population shoots up, the wolves start eating the deer, then the wolves population actually shoot up. So they're both cyclic, they actually go up and down in cycles. And the math model for such a system is this set of these two nonlinear differential equations. X is the predator population and y is the prey population. Alpha and beta actually the constants, the empirical constants. And notice that the variables of interest x and y, they're actually being multiplied on the right hand side. That is why this is a nonlinear differential equation. This is the famous nonlinear differential equation in mathematical biology called the Volterra-Lotka equation, and we will solve this Volterra-Lotka nonlinear differential equation in MATLAB like so. You go to the section for the biology application, left click anywhere here and press Ctrl Enter, and MATLAB actually uses the techniques that we discussed in the previous videos and solves these nonlinear differential equation using numerical techniques. And this is the plot of the prey, the deer population with respect to time, and this is the population of the predators, the wolves, with respect to time. This is a neat example of a MATLAB application for a biology problem. Moving on, we are considering an example from financial engineering or econometrics, and I have actually taken the S&P index for an arbitrary number of days. It really doesn't matter. I just took some arbitrary number of days and I plotted the stock price movement. So we are going to talk about mathematical methods in MATLAB that can be used for predicting the stock price a little bit ahead, in future. So the way to do that is you bring this stock data into MATLAB as a discrete sequence. So this is a discrete signal sequence, and we test for stationarity. This is a statistical test, and the discussion of test for stationarity is actually beyond the scope of this video, but know that sophisticated methods actually exist and we can use them in MATLAB to do the statistical test. And once we are satisfied that the condition for stationarity is fulfilled, we can model the whole stock movement as an ARMA process. ARMA here stands for autoregressive moving average process, and the discrete equation for an ARMA process is given like this. And we use techniques and theory from digital signal processing and linear systems analysis, and we actually predict the future movement of the stock using the techniques that I described above, and we can actually predict a little bit ahead in future. Okay, now we are coming to the data analysis part. In MATLAB, we can easily read in relatively large data sets and do pretty advanced math on the input data set. As an example, say you're doing some image processing on a series of images from a CT scan of the brain. So you've taken an image, or rather a series of images, and one image actually looks like this, and you are capturing dozens, tens, sometimes hundreds of images for analysis. And the way you would do data analysis on this image set is as follows. The first image is 1024 by 1024, say, and the second, third, etc., up to image 100. So this set of images is actually represented as a 3D matrix in MATLAB, and the data structure is something like this. It has 100 pages. Each page represents one image, which is 1024 by 1024. All right, so we can do lots of sophisticated math operations on this 3D matrix data set. We can, for example, do averaging, we can run edge detection algorithms, and we can do 2D fast Fourier transforms on the data set, and many other operations. So it is just one example of processing large data sets in MATLAB efficiently. Okay. Coming to the plotting part, MATLAB can produce simple line charts, multiple plots in the same figure, three-dimensional plots, say vector flow field diagrams of a gas flow or the exhaust of a jet engine, for example, histogram plots, polar plots, antenna signal strength diagrams, for example, 2D and 3D heat maps, pie charts, etc., just to name a few. In short, if you have the math model for the system that you're working on, MATLAB can probably simulate it. Also, MATLAB has pretty decent capabilities when it comes to handling large input data sizes, unless we are talking about matrices that are in the range of 100,000 by 100,000 elements. Okay, then it's probably time to go to Python. When it comes to plotting, MATLAB has superb capabilities. It can produce pretty much any plot that you can think of. Okay, that's it. Thanks for following this series called 1 Hour MATLAB so far. I hope this has been useful and interesting. Please leave your comments and feedback. Good luck with your MATLAB journey. Thanks for watching.